Hello everyone. Welcome to my talk on information theoretic optimal learning of Gaussian graphical models. I'm Sidhant Misra, and this is joint work with Marc, Vuffray, and Andrey Lokhov for my colleagues at the Los Alamos National Laboratory. The Gaussian graphical models are the usual Gaussian models that we all know, except that you think about the model as being on a graph. The sparsity pattern of the parameters theta is reflected in the sparsity pattern of the graph. What this does is give the Gaussian model the so-called graphical model separation property. For example, if you remove on the graph on the right, if you remove the variables x2 and x4, x1 and the rest are now disjoint. This translates directly to a conditional independence property, which is that conditioning on x2 and x4 makes x1 independent of the rest in the statistical sense. The Gaussians are also special in that the precision matrix, which is the matrix obtained by collecting these model parameters theta, happens to be the inverse of the covariance matrix. Now that's all about Gaussians. Let's dive straight into the problem statement, which is learning sparse Gaussian graphical models. Given n independent samples from some model, you don't know the model, so you don't know theta. Neither do you know the graph G, but you do know that it has a maximum degree D, so it's sparse. The goal is to recover the structure and the parameters of the model with some pre-specified level of confidence. Now, any method that is designed to solve this problem can be judged by two metrics, sample and computational complexity. I'll be primarily focusing on sample complexity, which is saying how many samples you need to perform this learning task. Now I have highlighted the word sparse to distinguish it from the more classical problem of learning dense Gaussian models, if you want, which is of course a very well-studied problem in statistics. Talking of sample complexity, Wang et al. In 2010 derived information theoretic lower bound for the problem, which reads that the number of samples required should be at least d log p over kappa squared, where kappa is this quantity on the right, which can be interpreted as the minimum normalized strength of a coupling. There are two curious observations. The first is that the sample complexity is log p, which is much smaller than the size of the problem itself. I suppose this is no longer surprising given that everyone is familiar with compressed sensing and sparse sensing in general, but it's still an interesting fact. The second is that the quantity kappa is scale-free. In other words, if you rescale the variables xi goes to alpha xi, it does not change kappa and hence does not change the IT lower bound either. Now, this is a natural property of the information theoretic lower bound, that it's scale-free, as illustrated as on one of the examples that I've given here on the bottom left. Suppose you are performing this hypothesis testing task of distinguishing whether an edge is present between x1 and x2 or not. So you're trying to distinguish between the two precision matrices given on the left. Now let's look at the same problem, but rescale the variables by some alphas. Now it turns out the KL between the pair of matrices, whether you look at the left or the right, remains the same, which means information theoretically speaking, there should not be a difference between the task on the left and right. This justifies why the IT lower bound should be scale-free. Looking at existing results in the literature, there has been a long series of results on this topic, starting from back in 2006. Now this 2006 is just after some of the major breakthroughs in the theory of compressed sensing happened. So people were excited in proving similar results for learning sparse graphical models. In particular, they were highly focused on showing that this similar surprising order log p sample complexity carries over to the case of learning sparse graphical models as well. If you look deeper into the proofs and the assumptions in these sample complexity guarantees, you see that there are many assumptions that are required. There are many of them. I have mentioned here a couple of more prevalent ones. Them being incoherence and restricted eigenvalue condition. These two and many of the other conditions that people usually assume all seem to have at least one common underlying factor between them. They all seem to imply that the condition number of the precision matrix is bounded, which is not something that appears in the information theoretic lower bound, which leads to the natural question, is the IT lower bound tight? Or is the bounded condition number necessary? We answer in this paper this question by constructing an algorithm called DICE, which attains the information theoretic lower bound as it is right now, without dependence on condition number, thus closing this sample complexity gap debate. Now, before going into the details of the method, I'd like to answer some few natural questions that often come up when we discuss this work with people. The first is that, well, there is a minimum bound on the edge, which is given by kappa. Does that automatically mean that the condition number is bounded? Turns out the answer is no, as specified by this example on the left, which corresponds to this 4-node graph on the bottom. If you turn up the intensity, the strength of this strong edge 1 minus epsilon, the minimum edge strength still remains kappa, it's invariant, but the condition number goes up to infinity, showing that these two quantities, condition number and kappa, are not only different, but can be also decoupled from each other. A second natural question is, well, why not directly test the graphical model separation property and then infer the structure of the graph from that? Now, testing the separation property is same as trying to test conditional independence from samples. And that's, for this case of Gaussian, same as looking at conditional correlations, empirical conditional correlations. It turns out that doesn't quite work, because the actual conditional correlation, for example, in the same case that I have shown on the left, if you look at the conditional correlation of 1 and 2 given 4, it scales as square root of epsilon. It's dependent on epsilon, which means that to distinguish whether this quantity is 0 or not from samples, you will need a precision of square root of epsilon translating to a sample complexity that has to scale as 1 over epsilon. Again, not something present in the IT lower bound. The third natural question is, well, maybe the whole condition number dependency is just an artifact of the proofs used in all these proofs to make it simpler and easier to flow, and it's not a real property of the algorithm itself. Turns out this is not the case either. It's not just an artifact of the proofs, as shown in this numerical experiment. We take this graph on the right. We have a way to rescale the variables with respect to each other, and we look at the performance of the methods with respect to this rescaling. Turns out all of the methods that I mentioned, at least we tested 3 of them, they are indeed sensitive to rescaling. So it's just not just an artifact of proofs. And some of them the probability of failure go to 1. They completely fail at recovering the graph when the rescaling reaches a certain value. Whereas one of the methods in our paper called slice is completely invariant under rescaling. So let's jump into the detail of what this method slice is. It's least squares with sparsity constraint. The first step of slice is indeed least squares with an L0 constraint. This is identical to what is done in lasso, except you replace the L1 prior by an L0 prior. Very natural thing to do. This regression is performed for each vertex I at a time, which is noted by this subindex I. But turns out this by in and of itself is not sufficient to conduct this structure recovery. You need this second step, which is geometric mean thresholding. It's a simple but rather critical step. So what is required is to take these regression estimates from 2 different vertex I and j, and then to decide whether the edge ij is present, you have to take a consensus between these 2 regression estimates, not just in any way, but in a geometric mean way, and that's important, and then perform based on the value of this quantity whether the edge is present or not. Why this whole method works? Let's look at a bit more detail into the steps. The first step is it's an L0 constraint, so it's looking at all possible candidate neighborhoods for a certain vertex I. For example, if you look at a candidate neighborhood A1, turns out that the minimum value in the objective is actually the conditional variance of xy given xa1. Of course, it's based on sample, so it's the corresponding empirical conditional variance. So you look at all such possible A1, A2, and so on, and the L0 constraint least squares actually chooses the A of size D that has the minimum conditional variance. Now, why this works? We have 2 key properties that are that make this whole procedure work. The first one is that the conditional variance is indeed minimized when you have the correct set of neighbors that you're conditioning on. And if you're conditioning on any other set that is missing one of your neighbors, so a wrong one, then it is higher than the minimum by at least a factor of kappa squared. The second key property explains why this whole geometric mean consensus is necessary and works, is that when you take this consensus, geometric mean, not only is the estimate itself scale-free, but the noise in the estimate is also completely scale-free of all parameters in the problem. So the statistics of the noise become scale-free. That's what I have tried to denote here by just writing plus 1 over square root of the n without any other factors. So the sample complexity of slice primarily depends on the first property, and it happens to be 32 d log p over kappa to the fourth. As you see, it is essentially information theoretic optimal, not depending on condition number, but has slightly worse dependence on kappa to the fourth instead of squared. And this happens because of the precision requirement of kappa squared from the multiplicative graph. To attempt to get the right scaling, we have another method which we call dice, which is a bit more complex. I'm not going to go into the details of that, but it has the flavor of an iterative testing, candidate neighborhood testing. You take every possible candidate neighborhood of size d, then you run it through a series of tests to see if it passes or not, and then decide on the correct neighborhood. Now, an important fact perhaps is that this method cannot be recast as a loss function minimization. It is an iterative method inherently by nature. Now, looking at the computational complexities of these methods, dice, since it's a double loop over the candidate neighbors, it's p to the 2d. I would like to emphasize that when you're looking at sparse graphs where d is order 1, this is in theory and computational complexity theory-wise, it's a polynomial time algorithm. It's not very small, but it is a polynomial time method that closes the information theoretic lower bound. A very interesting fact is there has been follow-up work by Kellner, Kohler, Meka, and Moitra very recently, where they have an improved version of dice which reduces the computational complexity and keeps the sample complexity. And they do so by identifying a more fine-tuned version of this key property 1, the multiplicative gap property. Now, looking at slice, it's a single neighborhood at 0 constant least squares. So it's order p to the d. But since it has 0 constant least squares, the important fact is that it can be recast as a mixed integer quadratic program, which makes it amenable to modern branch and cut solvers like Cplex and Kurobi, which I want to emphasize this fact that this can make it quite surprisingly efficient in practice. It rarely runs into what you would expect out of an exhaustive search. We illustrate this point by showing that you can solve, in the paper there is a numerical illustration showing that you can solve a not so small problem in very reasonable amount of time. So now, summarizing everything, you have the first series of results and methods that were developed that were all very efficient. They were order p squared, but they were missing the information theoretic optimality in terms of sample complexity. Now, I presented a couple of methods here which are optimal in terms of sample complexity, but they're not as efficient as order p squared time. So the question remains, can we have the best of both worlds? Now, thankfully, the authors that I mentioned on the previous slide, they have identified two special class of Gaussian models where you can indeed have the best of both worlds, them being a set of attractive models and work-summable models. And so this poses a very fundamental, being related to Gaussians, is fundamental and interesting problem of completely characterizing this intersection space. Like, what class of models allow for order p squared computational complexity while still being completely condition number free and hence attaining IT optimality? Well, that's what I would like to end my talk with. Thank you.